Um, Good afternoon, everyone. So today I will talk about my PhD work on developing a data-driven dynamic control scheme for antibody-producing CHO cell cultures in FedBatch. So this was done in this department, and it was in collaboration with AstraZeneca. So let's look at why do we need a new control for bioprocesses. So a bioreactor, although look very much like a chemical reactor, is fundamentally different because we are growing live cells in them. And all of the output that we observe are because of the dozens of variables that interact with each other inside the bioreactor. Although we know what kind of pH or temperature these cells like, we don't really have an understanding of what other values other variables like, which really makes it complicated. Because if you know what values certain variables like, you can do a set point control, which basically means you can use a PI or PID controller, and then say that, okay, this is a range we want the value to be within. And if it goes above or below that range, it takes a control action. But then what happens when we don't know what value they like? Then it becomes really complicated. So one of the major problems with what happens in a large-scale bioreactor is that they put the cells in them, especially the one that we are taking into consideration here is a CHO cell culture. So they go into the bioreactor for a period of 14 to 16 days. And then, so once you put all the things in there, you're going to add substrate every day, but then you don't know what's going on inside those bioreactors. You have measurements of certain variables, but by just looking at them, you can't really tell what's going to happen or how it's going to impact towards the end of it. So when you actually have the output at the end, that's the only time you know if everything has gone wrong, right or wrong. So that's not okay because we need to have better controllability for a bioreactor to keep the variance to a minimum. Especially for a bioreactor, what happens is when you have, so for the same amount of substrate concentration and cell density that you start with, you end up with very different amount of product concentration towards the end of it. So this is why we need to have a new control system for a bioreactor. How can we ensure consistent performance is one of the important questions. So the objective was basically this, to actually develop a model predictive control scheme for a bioprocess. And a biologics process basically has 3 different stages, starting with a cell line development where they optimize the cell type, media, etc. And then it moves on to the upstream bioprocessing stage where the cells are grown in large-scale bioreactors. And then it goes on to the downstream processing stage where they would extract the cells and get the products. So we were focusing on the upstream process development stage where we were working with large-scale bioreactor data. And then the model predictive control scheme, a typical model predictive control scheme looks like that. Basically, you have a model which describes the process, and then you have predictions, which is used for control calculations, and then you use the process output to make up for the, as residues that you add to the predictions. I will talk about this more, but then this is just to give an idea of where the whole project fits in. So in literature, you come across these kind of equations, which are mechanistic equations that explains an actual relationship that's going on within these bioreactors. But the problem here is that you will come across hundreds of these equations. The main reason for this kind of variability is because these equations are derived for a specific set of experimental conditions. So what happens is for a specific process type or a cell type, you would have one equation, which becomes not cross-compatible with a different kind of equation. And this is not okay because for us, we need, if you're looking at a bioreactor, you need something that's more applicable in a heterogeneous situation because we are growing different types of cells and different kinds of products, and then you need something that is applicable across the cell lines. And especially in this particular instance, for bioreactors, generally for CHO cell cultures, they use 4 different variables for control, which is glucose, glutamine, lactate, and ammonia. So they appear in the equation over and over again, but they really don't provide a lot of controllability. The main reason being you can add a lot of glucose, but this will give you a boost of cell growth in the initial part. But what happens is it causes accumulation of lactate towards the end, which means it's not a good control strategy. In addition to that, if you're adding a lot of glutamine, what happens is a lot of ammonia will build up, which is again a toxic byproduct. And because of the FedBatch nature of these cultures, you cannot really get them out as well. So these parameters, although we know their relationships and mechanistic relationship with each other, we don't really have good controllability just by using these. And that's why we wanted to see, okay, how can data help? Because there's a lot of data that's been collected from these bioreactors for decade of time, and then we have all of this just sitting around, and maybe we can actually use this for something really good to actually understand what's going on inside these bioreactors. So we wanted to see tackle different problems. We wanted to see how can we add more variables into the data matrix so we can understand more about this process, and how can we understand these variable relationships so we can use them for control, and then how can this help us develop new models, and how can these new models help with control. So these are the things that I will talk you through in this presentation. So coming back to the question, how can data help? All of us must have at some point come across this cell growth curve. So basically, cell growth has 3 different phases of growth, which is a lag phase, log phase, and a stationary phase. And what we often don't think about is that all of this is because of the variable interaction that happens within and between outside the cells. And if we can actually understand these variable interactions, maybe we can control them better. So we wanted to see if we can use historic data to learn more about the state of the culture, and we wanted to see if there is a specific interaction pattern, and if that pattern means a particular outcome, maybe we can design those interaction patterns to get the outcome that we want. And how can we make the best out of the data to ensure compliance? So let's see how can we learn from past cultures. So as I said, there's a lot of data, and it's good because we can actually represent the design space better. But then with bioprocess data, there are 2 kinds of data because of the difference in monitoring techniques. One being offline, and the other is offline. So online. So offline data basically means they have equal sampling intervals, and then they take data out. So you have 1 reading per sampling interval, whereas online data is measured throughout the duration of the culture, so it's continuous. So this is definitely more information in online data. But then there is a compatibility issue because of the differences in the frequencies in data collection. So what we wanted to make sure is that can we actually combine them together so we have a bigger feature space that we're working with. So can we use this online data and condense that so that it fits into the offline matrix, which basically means you want all of these hundreds of values that's being recorded every 5 minutes or even more frequently to just condense and fit into the offline data matrix, which corresponds to like 1 value per hour. So the general approach that's been used is averaging. But then averaging has several shortcomings. Especially in the case when there is variance. You cannot really capture when there is variance between the series. Here you can see 3 different series, A1, A2, and A3, where they have very different variance, but has the exact same average value. This can be very misleading, because if you are going to integrate this value into the data set, you're basically saying these this parameter for 3 different cultures had the same behavior, whereas in reality it did not. So here is another example of very different variants. And this is not really useful because we are misrepresenting at that point. So this is why we wanted to actually find a new method. So what can we do about this? So we thought about how we should deal with that. So basically, if a method that can actually take into account the temporal profile of this whole function, then maybe it can actually be a better representative. So what we did here was found a technique that actually would take the area underneath the curve. So in that sense, you can actually find a method that would condense the data, but also is a better representation of what's going on within these parameters. So at this point, the implication of this new method was that we could indeed find a technique that will actually distinguish 2 different cultures and their behaviors depending upon their temporal pattern. So in this way, we found a good method for data condensation, and now we have a larger feature space. So we have data coming from offline readings, data coming from online readings coming together, and we have a bigger design space. Now the next question is, how can we learn about these variable interactions? We have all these variables, but what does that mean? So we have seen in different fields how network theory has been really successful. So we thought, OK, maybe we can look into network theory for answers. So how can network help us? So network theory is very straightforward. We have heard about it a lot during this week. So basically, you start with a node. A node basically is an entity. And in this particular instance, these are different variables of a culture. And then you establish an edge between them when there is a relationship. And then you assign a weight when, depending upon the strength of that interaction. And then there are several different properties that you can explore after this, because there are properties like centrality, for instance, will give you a key variable on a specific day. This is very important if you're trying to implement a control action, because you want to know which variable to target when you're implementing control. And then similarly, concepts such as shortest path will tell you which node to target if you want to reach another particular variable. And similarly, edge weight is a concept which is useful because it will tell you the expense on the way to a target node. Because this is important because if you're trying to introduce a control action, the control action has to have as minimal impact on the system as possible, because you do not want to really create a lot of turbulence in the system, especially because they're cell cultures. So all of these kind of properties are really useful when it comes to understanding the variable interactions. And one of the main reasons we needed these kind of interactions was because of the two types of control variables that are present in a bioreactor. So basically, there are observables and there are controllables. So what I mean by observable is that we have readings for these variables, but you cannot really control them. For instance, ammonia is a byproduct, and lactate is a byproduct. If you want to reduce them, you cannot, because it's a FedBatch culture, and there is no way of taking them out, which means they are just observable. And there are controllable, such as pH or temperature, which you can actually alter from the outside. So we wanted to see, is there a way we can actually make the observable a controllable in some ways, as in if we can find a relationship between an controllable and an observable, maybe we can manipulate the relationship to control an observable just using those relationships. So these kind of things were really useful when it comes to network theory. So as I said, we tried to identify new variables for control, because now what we wanted was the existing variables were not really useful, so we wanted to find new variables for control. And indeed, that's what we did. And then we constructed models by using the ones from literature and the ones that we identified from network. So we basically built symbolic regression model. We heard about them in an earlier talk today. So these models are actually useful because they are not black box models. They are equations which we can actually optimize using an optimizer. And that is important because if you want to do a control action, you need to be able to optimize an equation. So what we did see was that the predictors from network performed better, and they also worked across different cell lines, product types, and culture conditions. So the main reason for this is because the relationship that we extracted came from heterogeneous data sets. So all of those kind of really helped in predictions in the later stages. So now what we had was we can look at the variables and see what the culture is, what the output is going to be, which is great, because until that point, we only had readings for variables and we didn't know what it meant. But now we can look at the variables and tell, okay, this is what it's going to do today. But then for control, it's also important to know what it's going to do tomorrow, because we need to have an expected trajectory, because previously we didn't have one. So basically, now that we had equations, for instance, here for viable cell density, which is a function of certain variables, for the next time point, it would be the same function, but the value of the variables would be the value of those variables at the next time point. So how can we do that? So for this, I again looked at networks. So basically, for every variable, for a particular variable, I looked at the different variables that it had interactions with on all the days of the culture. So I identified those variables along with the value of that particular variable A at time point t, and then I used SVMs to train so that it will predict the value at the next time point. And this actually did work out pretty well, because so once we have that value of that variable, you can insert it back into the equation and then get the predicted value of the outcome. So this worked out quite good, because we could actually predict the different variable values. And then once we inserted that into the viable cell density equation, it did give us a good prediction. So at this point, we had two things. We can look at the variables and tell what is going to happen today. We can also look at the variables and tell what's going to happen tomorrow, because then we can actually understand where the culture is headed. And if it's not headed in the direction we want it to, we can actually implement a control action. But then how do we do this? So does predictability always mean controllability? So that's obviously a question. So we wanted to see how can we demonstrate control. So for this, I had to introduce a perturbation, because it was a simulation. I had to introduce a perturbation and see how the system behaves to perturbation. And then I wanted to see how we can control that. So basically what I did was I picked a culture, used the models to predict the value of the response variable at the next time point. So that was considered as the expected value. And then I introduced a small perturbation at time point t, which is known to be detrimental. And then I use the same models to predict the viable cell density value at the next time point. So this is the observed value, and this is after perturbation. So obviously, it's going to be lesser than the expected value. So the aim is to see, can we actually bring this value back to the expected value? So this is what the control trial looked like. I picked a culture, as I said, introduced a perturbation, and then we observe what happens to the response variable when that perturbation happens. And then we look at the network on that specific day to see what the variable interaction looks like. And then you identify the best target variable on that day, depending upon so many different parameters, such as shortest path, weight, etc. So you know which is the best target variable. And then once we have that, you can identify a mathematical relationship between these variables using symbolic regression models. And then once we have that, you can use an optimization algorithm, which will then tell you how much of the value you have to change to bring the system back to the expected value. And this is a powerful thing to have, because previously, all we had was a bioreactor running on its own. We didn't know what's happening. We had to wait until the harvest day to say what the outcome would be. But now what we can do is we can actually model, we have already modeled the system so that it will tell you what the expected trajectory is, and if it's actually not following the expected trajectory, it will also tell you how you can, what variable to be changed to actually stick to that trajectory, because previously none of this was possible. And this is all possible because of the data, because we are learning from the data, we are calculating the expected trajectory, and this calculation of expected trajectory is done like iteratively as well, so that the uncertainty is minimum. And then how is this helpful? So without a control action, what happens is every time point it will deviate a little until you end up with a large difference in the productivity, whereas with control action, you have a more tightly controlled trajectory. This is not an actual graph, just a visual representation to show how it would work. So what does this mean for a front-end user? Is basically once they set up a bioreactor and they measure the value of the variables at particular time point t, and they enter into the system, and the system would then predict what the outcome is going to be at the next time point. And once they observe the values at the next time point, what it would happen is it would check if the observed value is less than the predicted value. And if that is the case, then the system would suggest a control action to be implemented at the next time point. And what we have as a result are cultures with less variability that follows a tightly controlled trajectory. And this is good because a controllable system is an optimizable system, because then we can make them to produce more as we require. And this is what it looks at the back end, but that's for nothing to worry about for now. And I would like to thank my supervisor, Dr. Duiku, who has since moved to UCL, Professor Alex Ruth here in Cambridge, Dr. Aicha and Matthew at AstraZeneca for all their intellectual input, and BSc group here at Cambridge, colloidal dispersion group here in Cambridge, DigiSmart Bio at UCL, AstraZeneca for the funding, Department of Chemical Engineering for all the infrastructure and support all these years, and Churchill College for all of my life in Cambridge. And thank you very much. I'll take any questions.